This video explains one application of the Bernoulli's equation, that is the Venturimeter. Let's start. So Venturimeter is a device used for measuring the rate of flow of a fluid flowing through a pipe. So rate of flow is measured by Venturimeter. It consists of three parts, that is a short converging part, a throat and a diverging part. And it is based on the principle of Bernoulli's equation. So let's derive the expression for rate of flow through Venturimeter. So in the figure you can see a Venturimeter which is fitted in a horizontal pipe through which a fluid is flowing, say water. Okay, so here you see the pipe, the Venturimeter is connected here. So we said that the Venturimeter has three parts, a short converging part, a throat and a diverging part. Converging means coming together and diverging means going in different directions. So this part is the converging part, this part is the diverging part, and this is the throat. So inlet is the part where the fluid is entering the Venturimeter. So the fluid is flowing in this direction. So here we have the inlet, the converging part, then the throat. So if we see the inlet and the throat, you can see that the diameter of the throat is lesser than the inlet. And we have marked sections 1 and 2. Section 1 is at the inlet and section 2 is at the throat. So let's see what is marked in the figure. D1 is the diameter at the inlet or at section 1. P1 is the pressure at section 1. V1 is the velocity of fluid, that is water, at section 1. A is the area of cross section at section 1, that is A1, which is equal to pi by 4 into D1 square. Okay, it is a circular cross section. And H is marked here. H is the difference in pressure between points 1 and 2. That is the pressure difference in pressure head or difference in pressure energy. And if we consider section 2, the same notations are there. D2 for diameter, P2 for pressure, V2 for velocity and A2 for area of cross section. So let's apply Bernoulli's equation to section 1 and 2. We get P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Okay. We assume that there is no loss of head. So H is not considered here, right? H is not there in this equation. We consider it as an ideal fluid. As the pipe is horizontal, Z1 is equal to Z2. Before, in the pictorial representation of Bernoulli's equation, you have seen that Z1 and Z2 are the potential head. So if this is equal, it is cancelled, right? So only 4 terms are there now. So if we bring P1 and P2 to one side, we get P1 minus P2 by rho g is equal to V2 square by 2g minus V1 square by 2g. P1 minus P2 by rho g on the left hand side, it is the difference of the pressure heads, right? P1 by rho g is pressure head, P2 by rho g is also pressure head, and so P1 minus P2 by rho g is the difference of pressure heads at section 1 and 2. So that is given a common notation, that is H. Okay, that is marked in the figure also. Okay, P1 minus P2 by rho g is equal to H. Okay, so on the left hand side we substitute H. So this equation becomes H is equal to V2 square by 2g minus V1 square by 2g. Then apply continuity equation that we know as A1 V1 is equal to A2 V2, where A1 and A2 are the areas of cross section and V1 and V2 are the velocity. Okay, so we find out V1 is equal to A2 V2 by A1 and we substitute V1 in equation 6.6, that is this equation. So V1 is substituted in this equation. So the equation becomes V2 square by 2g minus A2 V2 by A1, that is this quantity, the whole square, by 2g. So this finally is simplified to in the terms of V2, that is V2 square is equal to 2gh, h goes to the other side and V2 comes to the left side. 2gh multiplied by A1 square by A A1 square minus A2 square. Okay. So we got V2 square is equal to 2GH into A1 square by A1 square minus A2 square. So this becomes square root of 2GH into A1 divided by square root of A1 square minus A2 square. Okay, the expression of V2. So discharge Q is given by A2 into V2, right? That is, we can substitute for V2 here. V2 we have got from this equation. So that is substituted here. So that becomes Q is equal to A1 A2 into square root of 2GH the whole divided by square root of A1 square minus A2 square. So this gives the discharge under ideal conditions. That is the theoretical discharge. Okay, ideal conditions means all conditions are ideal or perfect. There is no discontinuity or deformity in our assumptions or in the real conditions. But real conditions cannot be like that. Real conditions cannot go according to theory. So we have the real conditions giving us actual discharge. An actual discharge will always be lesser than the theoretical discharge. So to obtain actual discharge, we have to multiply the equation of theoretical discharge with a coefficient. That coefficient is called coefficient of Venturimeter, that is CD. And its value will be always lesser than 1. That is, theoretical discharge will always be lesser than the actual discharge. Actual discharge is given by CD into theoretical discharge. That is A1 A2 into square root of 2GH the whole divided by square root of A1 square minus A2 square. And the value of H is given by a differential U-tube manometer. So we have different cases for obtaining the value of H. In first case, the liquid in the manometer is heavier than the liquid flowing in the pipe. In that case, the equation is X into SH by S0 minus 1, where X is the difference of the level of heavier liquid in the U-tube and SH is the specific gravity of the heavier liquid, S0 is the specific gravity of the lighter liquid which is flowing through the pipe. In case 2, the manometer has the lighter liquid and the pipe has the heavier liquid. So the equation becomes X into 1 minus SL by S0, where SL is the specific gravity of lighter liquid, S0 is the specific gravity of the heavier liquid in the pipe, and X is the difference of the liquid in the U-tube. Okay. We have case 3, which is the inclined Venturimeter. That is, there is level difference between sections 1 and 2. That is, Z1 is not equal to Z2. Okay. Earlier we said that H is equal to P1 minus P2 by rho into G. But this is not true now because Z1 is not equal to Z2. So H is equal to P1 by rho G plus Z1 minus P2 by rho G plus Z2. This equation did not have the Z term because Z1 was equal to Z2 before. Because the manometer was, the Venturimeter was horizontal, but now it is inclined. So Z1 is not equal to Z2. So this term has Z2. So P1 by rho G plus Z1 minus P2 by rho G plus Z2 is equal to X into SH by S0 minus 1. Similarly, for inclined Venturimeter in which differential manometer contains a liquid which is lighter than the liquid flowing through the pipe. The case 3 says that the manometer has heavier liquid. So the equation is here. Case 4 says that manometer has the lighter liquid. So the equation becomes this. Okay.